Hello everyone, and welcome to this talk about a multi-language static analysis of Python programs using C libraries. I'm Raphaël, Monat, and this is joint work with Abdelraouf, Ouadjaout, and Antoine, Miné. The goal of our work is to perform static program analysis, to detect bugs or prove the absence of them. So for example, in the program on the left, we'd like to prove that the first call is correct, but that the second call will raise, in every case, a type error exception when we'll try to add the string a here with the integer 0 at the first iteration of the loop at line 4. And conversely, we'd like to prove that the program on the right is free of runtime errors. The string length function is called on a valid string and that there are no overflows over the integer addition. So we'd like our analyzer to perform an inference of program properties, and here we target runtime errors. We want our analyzer to be automatic so that no expert knowledge is required to run it. We want it to be semantic, so based on a formal modelization of the language. And we want it to be sound so that it covers all possible executions. And Python has quite a few features making its static analysis an interesting target. It's growing in popularity, and it's an dynamic object-oriented programming language, which has a few features. One of them is a complex semantics. So here is a flowchart of the semantics of the addition of two expressions E1 and E2, and it depends on complex conditions involving the types of the terms and can call two different methods, either this one there or this one here. And our goal today is to analyze Python programs with C libraries. This is important as a significant number of Python libraries are written in C. This might be to bring better performance in the case of numerical computing libraries such as NumPy, or to provide library bindings with system libraries. There are, however, a few issues when combining C and Python. The first is that the languages have different values. So for example, integers are unbounded in Python and bounded in C. You have different object representations. Runtime errors are catchable exceptions in Python, but they usually terminate the program in C. And you also have the garbage collection to manually handle on the C side. So here is the outline of this talk. We'll first start by showing a concrete example of Python program interoperating with some C code and how we could tackle its analysis. We'll briefly talk about the concrete multi-language semantics, and then we'll highlight how some design decisions of our analyzer called MUPSA eases the lifting to a multi-language analysis. So let's start with our example. So this is a toy example of a counter object defined in C. It has a header here to be considered as a Python object, and then we add a special field which is the count of the counter instance, which is a signed integer. We define two methods over this counter object, something to increment the counter. So by default, we'll increment by I, which has value 1, but this value can be overridden if passed as an optional argument to the method. We also have a getter, which takes the C integer value here and transforms it into a Python integer using this built-in API function. And here is a sample client code for the counter library. So first we instantiate the counter here. Then we pick a number between 0 and 127. We increment by 2 to this number we picked, -1. Then we increment again, and we store the Python integer corresponding to the result of the counter in this variable r. So let's see what happens. If power is less than 30, then we have the expected result, which is that r is 2 to the power. However, there are other cases. Since Python integers are unbounded, but C ones are, we may encounter conversion errors. And the error messages depend on whether power is greater or equal to 64 due to a double conversion. And finally, there is this really edgy case when power equals 31. So what happens in that case is this first increment is correct, but the second increment here, which is done at line 13, will do an integer wraparound on the C side. So in the end, we get a negative result, which is really unexpected for pure Python developers. So there are a few ways we could avoid analyzing this C code. One way would be to use the type annotations of Python as stubs for the native code. So in the case of our running example, we could say that the incrementation method has an optional argument I, which is an integer and has default value 1, and that the getter returns an integer. There are, however, a few issues with this approach. First, there is no way to annotate for the potential rate exceptions by each method, so we'll miss errors and reduce the soundness guarantees of our analysis. These type annotations only mention types and would be imprecise in the case of a value analysis. But this is actually a popular approach, and there is even a typeshed project which provides type annotations for the standard library. And actually this was the approach we used in our Python analysis up until this work to support the libraries that used native C code. Another way to support it would be to rewrite it into pure Python code. But again, some effects just can't be written in pure Python, and we would lose soundness. So the main drawback of the current approaches I've presented is that there is no analysis of the real C code. Since there is no analysis, the approaches we've seen are not automatic, and they are not sound since they do not take into account some of the effects. By contrast, our approach is able to analyze both the C and the Python sources, and the analysis will mimic the switches between languages just as the execution does. It builds upon previous analysis of C and Python, and it detects runtime errors in Python, in C, and at the boundary between the languages. If we go back to this example, here is the result of our analyzer. So we can detect the integer overflow that happens here, and the potential conversion errors between Python integers and C integers that happens at line 6. So let's talk about the concrete multi-language semantics. Semantics builds upon the Python and C semantics and delegates most of the work to these semantics. It only defines the API, that is, the calls between the languages and value conversions. Since we build upon the semantics of the two languages, each language has a view of the heap. Through our careful choices, we can make these representations disjoint and complementary. We introduce the notion of boundary functions, which ensure that views are synchronized when objects switch languages. There are a few limitations to our current approach. We do not support garbage collection. C code can only access the values of Python objects through the API. And we've performed this semantics through manual modelization from Python's source code. You can find more details about the semantics in the paper. Now let's talk about MOPSA, which is the multi-language analyzer we use. So MOPSA provides a language-agnostic framework for relational static analysis, and it features a loose coupling of abstract domains that can be composed and cooperate to improve the precision. So here are schematic representations of the domains used in an example Python analysis and the domains used in a C analysis. And as you can notice, the abstractions of dynamic memory allocation here, of numerical domains here, and iterators here and there are shared in what is called universal domains. And thanks to MUPSA's design, combining both analyses to obtain the basis of the multi-language analysis is just a matter of recombining the abstract domains. In particular, the so-called universal domains in blue are shared by the two languages. Let us illustrate this sharing on our learning example. During the counter instantiation, at line 4 here, we will end up initializing its count field with 0. So we perform quite a few abstract evaluations here and perform this assignment in the end. So this is stored in the interval domain here, and similarly, the value of the power variable at line 5 will also be stored in the same domain here. So sharing the numerical domain provides additional precision in the case of relational analysis. And you can also note another thing, which is that the abstract information about the counter class is spread across different languages. So here, for example, and there. So we have run this multi-language analysis on a few libraries that we found on GitHub. These are real-world libraries that average 412 stars on GitHub. Since we perform a whole program analysis, we use the tests provided by the libraries as driver code for analyzing them. So you can see that we're able to scale to programs that have up to 5,000 combined line of code in a few minutes. Here is the selectivity of the C analysis. So this is the number of operations proved safe compared to the total number of runtime error checks. So in C, this includes integer overflow checks, invalid pointer differences, and so on. And here is the selectivity for the Python analysis. So this includes type-related errors, division by zeros, and that kind of stuff. And here is the average number of transitions between the Python code and the C code per test. So this means that our driver code is truly testing the multi-language capabilities of our analyzer. So in conclusion, previous works focused on the JNI, the Java Native Interface. They all performed, one way or another, a static translation of some of the native code's effect back into the Java analysis. Contrary to that, our approach performs dynamic switches between the analysis of Python and C. It builds upon previous C and Python analysis, and some abstract domains are shared. Thanks to MUPSA, each language has different abstractions, but these abstractions coexist and collaborate. In future work, we'd like to analyze larger applications, validate typesets annotation, and apply our approach to other multi-language settings, such as the GNI. Thank you for listening, and I'll be happy to take any questions that you may have.